In this video, we will look at expressing equations of lines in the 3D space. There are two forms for which we can express the equation of a line in, and we have to be familiar with both and how to convert in between the two forms. The first and more important form is the vector form. In all subsequent calculations involving lines, they will be performed using the vector form. To understand how the vector form is derived, we start from an arbitrary line which is parallel to a certain direction vector d. The line passes through a known point A, and we let a random point on the line be point R. To move from point A to point R, we simply have to displace point A by a certain displacement vector which is a multiple of d. For example, we can displace point A by just d, or we can displace point A by 2d, 3d, and so on, and we will arrive at different points which are on the line. Therefore, the position of point R can be used to describe any point on the line and is thus the equation of the line, which is expressed as this form over here. In this format, L represents the name of the line, R is a general random point on the line, which is equivalent to the point with a coordinate of x, y, and z. A is a point on the line that we must know is position vector. Lambda is a real number which brings us from point A to different points of the line by multiplying with vector d, and d is the direction vector of the line. In example 1, we are asked to write down the equation of the line that passes through point A. So I have a line that passes through a certain point A with coordinates of 1, 2, and 3, and it is parallel to the vector 2, 4, minus 5. And therefore, the equation of this line can be written as R equals to 1, 2, 3 plus lambda 2, 4, minus 5. And of course, we must always specify that lambda is a real number. In example 2, we are now asked to find out the equation of a line that passes through 2 points, point A, 1, 2, and 3, and point B, 3, minus 1, and 2. So what we have to do now is to identify that the direction vector of the line can in fact just be vector AB. So it is going to be OB minus OA, which is 3, minus 1, 2, minus 1, 2, 3. And this gives us 2, minus 3, minus 1. And therefore, we can write down the equation of the line as L is such that R equals to 1, 2, 3 plus lambda 2 minus 3 minus 1, where lambda is a real number. Of course, instead of using point 1, 2, 3, you can also make use of the point 3 minus 1, 2, since point B also lies on the line. In 2D space, we have learned about the Cartesian equation of a line, which is simply y equals to mx plus c. However, in 3D space, the Cartesian equation is not as simple. To obtain the Cartesian form, we will need to first find out the vector form of the equation and perform a conversion to transform it into the Cartesian form. And I'll illustrate the conversion process using the following example. Now, if I have a line such that it is R equals to 1, 2, 3 plus lambda 4, 5, 6, then what I can say is x, y, z equals to 1, 2, 3 plus lambda 4, 5, 6. And I can expand out this system of equations into x equals to 1 plus 4 lambda, y equals to 2 plus 5 lambda, and z equals to 3 plus 6 lambda. And next, I can make lambda the subject for each one of them. I will get lambda equals to x minus 1 over 4. Lambda equals to y minus 2 over 5. or lambda equals to z minus 3 over 6. And since we know that all the lambda must be equal, we can say that x minus 1 over 4 must be equals to y minus 2 over 5, which must be equals to z minus 3 over 6. And this is the Cartesian equation of a line. In example 3, we are asked to form the equation of the line that passes through point A and it is parallel to the vector 2, 4, minus 5. So let's start by writing down the vector form of the equation of the line, which is L such that it is R equals to 1, 2, 3 plus lambda 2, 4, minus 5, and lambda is a real number. So let's change R into x, y, z. I will get x, y, z equals to 1, 2, 3 plus lambda 2, 4, minus 5. Again, lambda is a real number. Next, I can form the equation x equals to 1 plus 2 lambda, y equals to 2 plus 4 lambda, and z equals to 3 minus 5 lambda. And if I'm going to make lambda the subject for all of them and equate the lambdas together, I will end up with x minus 1 over 2 equals to y minus 2 over 4 equals to z minus 3 over minus 5. And this is the Cartesian equation of the line.